So we were all very disappointed. However, there is an upside of that. It turns out that they do get to the nervous system, and they seem to have an influence on the environment of the central nervous system that may allow the progenitor cells that are in the brain to work better. And with that in mind, there actually are going to be clinical trials forthcoming with so-called bone marrow or mesenchymal stem cells. Again, I listed here how to get them to the central nervous system. Doing multiple transplants into the brain is going to be extremely difficult, so that intravenous or injection into the spinal fluid is a much more reasonable approach. And here I quote from a paper, and I've highlighted the message here. When people in this group, having Jean Martino and Michael Schwartz, and the Italian group from Milano, and the bottom line is when they have injected, as I mentioned, these kinds of these either neural stem cells or bone marrow stem cells, the feeling is that these cells, when given intravenously, are not becoming the mature cells, but they're allowing the other cells to work better. And the other feature of this, which was pointed out by Tamir Ben-Ur in this paper, is that they also have the feature that they may block some of the immunologic responses that may be damaging the nervous system. So these progenitor cells both are making a better milieu for the progenitor cells to work in the brain, and they also seem to be shutting down some of the immune attack phenomena. And so we may have been using initially these cells for the wrong reason, but now we are building actually a rationale for using this. And if you take the lowly mouse and give it the best model we have of MS, this is called EAE, that in that model system, injection of these cells has a behavioral benefit to the animal, and we're going to hear more about this in the clinics because this is feasible. Now, what if we turn to the issue of within the brain, can we use this endogenous repair strategy? So you can't do anything unless the cells are there, and then we would have to promote their activity, and then we still have to figure out that if we knew which molecules would promote their activity, how to deliver those molecules. Now, this is an MRI scan, and the reason I put this in, this is the tissue that we work with in our research lab that we get from the operating theaters, where we have surgeons who are trying to cure epilepsy by removing certain parts of the brain. And if you see this white area here, and the white arrows here show you this area is removed, this is the area that we've used, and other people such as Steve Goldman at the University of Rochester and Neil Scolding in Great Britain have used. The community that's studying the neural progenitor cells in humans largely is working from this kind of material, and that's why I put this slide in. If you take that material and you derive all the cells that are in that brain and put it into a tissue culture system, and you say, can I identify the presence of progenitor cells? I mentioned this A2B5 marker, so we use this. Are there any cells in your tissue culture that express A2B5? Here they are. And Steve Goldman initially, and then we've confirmed it in others, that if we take the tissue from where I've shown you and analyze the cells, that 1% to 3% of the cells have this marker indicating that they are potential progenitor cells. There are also some cells that are even earlier in development also present in the adult human brain. Steve Goldman has done the very important experiment that he's taken these cells with this marker and he's transplanted it into mice that have no myelin. They have a genetic problem, so they don't have myelin of their own. And you transplant these cells into the mice. These mice then you will get myelin formed in the mouse brain. Now, one of the bottom lines we always have to consider is there a basic difference between mice and men in terms of the capacity to remyelinate? But at any rate, these cells are capable of producing myelin in the dysmyelinated animal. Now, another question that we don't know an oligodendrocyte, which is the cell that makes the myelin, it actually puts out its arms and myelinates multiple nerve fibers. If you damage one or two of those arms of the cell, why doesn't this cell remyelinate? Why doesn't it just put its arm back? If it's got 50 arms and you take away 5, if it's got 45 arms, why doesn't it just regenerate the 5 arms? And if you take those cells from the adult human brain and put them in culture, they put out their processes again. So even those cells have an intrinsic capacity to put out processes that have myelin components. These cells, I'm not sure that mice, their cells behave the same way. Okay, now one of the things I did put in as well, one of the important issues that we have to consider in MS, and maybe one of the things that's limiting why the repair process, is it possible that the progenitor cells themselves are being injured as part of the disease process. And it may be that part of our anti-immune therapies hopefully will protect against damage not only to the myelin, but maybe damage to the progenitor cells. And this is some early work done by Hans-Peter Hartung, who's actually the president of ECTRIMS and his group, that several years ago identified that people with MS may have antibodies that actually could damage the progenitor cells. And this is a very active area of research now. So I've tried to tell you that at least there seems to be the cells present in the brain and that they have some kind of capacity, at least when transplanted into animals. So how are we going to improve the function of these cells? Peter Rickman briefly mentioned, but the neurobiologists who study how the brain develops normally have identified a whole series of molecules that promote the maturation of progenitor cells and how they form into their final mature product. And many of these are called neurotrophins, and they all have names as well, listed here. And the neurobiologists know a great deal about these molecules. Importantly, that these molecules act on specific receptors. Once you have receptors, then the pharmaceutical industry becomes interested because they may not have to use the natural molecule, but could you find molecules that act on these receptors that would stimulate these progenitor cells to survive, to mature, and then to perform their functions. And that kind of search will be ongoing. Now, in case I don't remember to come back to this, Peter Rickman mentioned an extraordinarily important issue and that he and his group and others work on now, and that is for the therapies in MS we currently use, the anti-inflammatory therapies, there is tremendous interest in the development of drugs because we have an easy readout to say whether the drug is working. The MRI measuring the lesions on MRI allow us to tell very quickly whether a drug has an anti-inflammatory effect. The clinical community is going to have to come up with a measure to know whether any of the interventions of these drugs that we're now postulating are really going to have an effect or not. Because if we're going to have to wait 3 to 5 years of testing people, some of whom are on the real drug and some are on the placebo, it's going to be a very difficult issue to get interest in this field. Hopefully, if we, just like with the anti-inflammatories, once we had proof of principle that one drug worked and we had a technique to measure, the interest in development went up tremendously.